Dear student, warm welcome to NPTEL Phase 2 program video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This is Module 13 and lecture number 60, Designing with Geofoam. I will now focus the recap of the previous lecture. Advantage of the geofoam, disadvantage of the geofoam, and comparison cost of construction method, function of geofoam, application of geofoam as a compressible inclusion. Now, I will address the application of geofoam as thermal insulation. The geofoam can be used as a thermal insulation beneath the building floor slab, roof and ceiling as well as outside of concrete wall. It is used exclusively for packaging of electronic goods and fishes. It is also used as a coffee container as well as in industrial building, houses and garages, etc. Geofoam has excellent heat insulation properties. The hot and cold temperature can be diminished with the aid of geofoam. In conventional method, the foundation of storage building is made of concrete slab on gravel for thermal insulation. Alternatively, a layer of geofoam can be used, replacing the gravel layer to diminish the cold layer or hot. The thermal resistance R as well as coefficient of thermal conductivity K of geofoam play very important role. So, we will just use the geofoam alternative to the gravel or the brick, and we will check up how we can replace the gravel with the geofoam and how there is a variation of the temperature, either it is cold or the hot. This example, a building has a base area of 30 meter into 20 meter. The thickness of concrete floor slab is 300 millimeter. The floor slab can be rested over the gravel or brick conventionally or over the geofoam alternatively, and temperature difference is 25 degree centigrade. The thickness of geofoam is 200 millimeter. Thermal resistance of geofoam is 30 degree centigrade meter square per watt, and thermal resistance of concrete R is equal to 0.78 degree centigrade meter square by watt, and thermal resistance of brick R is equal to 1.1 degree centigrade meter square by watt. So, it is like that building, the building away from the temperature from the ground and determine the heat flow without and with the geofoam. So, sometimes we require to storage some vegetable or any other kind of the material to protect. So, conventionally we build up a reinforced concrete slab, and below that we provide with the gravel, and then you are constructing the building on the top. And how you can see, this is the with the traditional system we adopted the gravel as a material. And in the case of the conventional method, that when the temperature moves from the ground towards the building, then you can observe that what kind of the heat flow are occurring and how you can measure the heat flow. And if the heat flow is on the hard side, then there is a possibility of the wastage of the vegetable or other kind of the material. But alternative to that system, that if we use the geofoam alternative to gravel or the brick, and then if you can construct a building for the storage here, and then we will see that how the heat flow with the geofoam material. So, here is a solution. Heat flow is H. The equation is H is equal to AH delta T by R, where H is equal to the heat flow, AH is equal to cross-sectional area of the heat flow, delta T defines in the temperature across the material, and R is equal to thermal resistance. Now, when we use the traditional method, that means with bricks or the gravel, so we know the equation heat flow H is equal to AH delta T by R. Here H is the area, that you know 30 meter into 20 meter is equal to 600 square meter. And this R of concrete, I say that thermal resistance of the concrete is equal to 0.78 degree centigrade meter square by watt. Similarly, thermal resistance of brick, R of brick is equal to 1.1 degree centigrade meter square by watt. And temperature difference delta T is equal to 25 degree centigrade. So, you can write H is equal to AH means area, that is 30 into 20 into delta T, temperature difference is 25, this divided by the R. R is thermal resistance for the concrete as well as thermal resistance for the brick. This is the traditional method, where there is a concrete and also brick or the gravel. So, this is 0.78 R for concrete and 1.1 for the brick. So, this will be equal to 600 into 25 divided by 1.88. So, this will give 7978 watt. So, here heat flow you can see with the traditional 7978 watt. Now, if we adopt the alternative system, that is the geofoam. With geofoam, let us say thermal resistance of the geofoam is 30 degree centigrade meter square by watt. So, H its heat flow will be equal to, you know that equation, here it will be the 30 into 20 into 25, this divided by this, you know what is the resistance for, what I mentioned also that here, that R for the concrete. So, R for the concrete is 30.78 plus that plus is 30. So this will give you that 600 into 25 divided by 30.78, this is 487 watt. Therefore, saving the heat flow will be equal to 7978, that is here 79, that 78, this divided by this minus 487 watt. That means the saving in the heat flow is 7491 watt. So if the geofoam is used instead of the gravel or the brick, heat flow will be 16 times less. So you can save the energy, you can save the heat. It can be inferred that geofoam is a very good insulator and cost effective alternative material. Now I will discuss the installation of the geofoam. Now you require subgrade preparation. That site should be clear from all type of debris, stone, stumps, etc., and compact it and level it. Excavate the existing soil if required. Dump a sand pad before placing geotextile and leveling the course of maximum thickness of 100 millimeter. At design engineer discretion, unroll the geotextile directly over the very soft subgrade. Geofoam block is laid on the prepared subgrade. The geofoam is fixed one with another by butt joint. Sometimes no need for vertical joint, as coefficient of friction between the adjacent geofoam block is adequate to prevent the slippage between them. No compaction is needed. When the geofoam is required for trimming and cutting, this is easily done using a chin saw, nut oar or hard saw. The geofoam block can be fixed together using a galvanized mild steel plate with sharp pointed multi-barbed connector up and down. So it is like this I am giving one small model. This is the kind of the galvanized mild steel plate, and this is the sharp pointed. This is multi-barbed, this is multi-barbed connector, and up, and also you can see up and down like this. Suppose if this is the geofoam material and you wanted to connect this geofoam material one with the other, you can place it, okay, and then you can put the other material like this, or you can place one by one, and also you can join like this. So it can be jointed like this, okay, and then you can place the another also, if it is required, you can place the another also the geofoam. So that should not be any slippage. So this geofoam block can be fixed together using this galvanized mild steel plate with sharp pointed multi-barbed connector up and this down. So Here is the spike at the connector of EPS geofoam block after EPS EDO 1993, Negoci 1997. Here also you can see that this is 150 millimeter and this distance is about 100 millimeter. This is 25 millimeter, this is 25 millimeter, this is 150 millimeter, this is 25 millimeter, this is 25 millimeter and this is 200 millimeter. You can see this is the point rate that sharpened that galvanized mild steel on the top as well as in the bottom. So, like this kind of spike, or this is what I this. So, you also this is for the model which student have made this. So, it is like a 5 centimeter and this is 2 centimeter and this also the 2 centimeter. This spike got connected for the EPS geofoam block. So, you can use this kind of the spike guard for connecting the geofoam material one with the another. The coefficient of friction between the geofoam block is 0.5 approximately. 2 spike guard per block are used to control the slippage one over another to build a structure. The geofoam block are held against horizontal movement and hold tight. It is necessary to protect the geofoam from petrol and other solvent. A geomembrane of minimum thickness 2.5 millimeter can be laid over the geofoam. So, geomembrane of 0.5 millimeter thickness can be laid over the side slope for the protection. So, when there is a possibility for any leakage from the petrol leakage, then you can provide with the geomembrane material which can protect the geofoam. No construction equipment should be placed on geofoam until minimum 450 millimeter of fill material or soil is placed over it. If the geofoam is damaged due to any load, it should be discarded. Geofoam should not be placed exposed to sunlight for more than 1 month. In such case, it should be covered with tarpaulin or the plastic sheet to prevent it from the ultraviolet light. There should not be any open flame near the geofoam. Geofoam should be ballasted during the wind as placed manually because it is a very light material. The geofoam is not harmful during raining or snowing. Now, I will discuss the design of a magnet using geofoam. So, you have now the earlier idea that how the geofoam is to be installed, and also you have some idea how the geofoam can be used as a thermal insulation which can minimize the heat flow. Now, we want to use this geofoam for the construction of the embankment. Now, when the soil is very soft, before the commencement of construction, it is required to pre-compress or preload the compressible soil to accelerate the desired settlement by long surcharge period. It is a time consuming process. Otherwise, normally we go for pile foundation which are required to reduce the settlement and improve the bearing capacity of the soil. It is very expensive. Alternatively, geofoam block can be used to reduce the pressure over the soil. It is economically faster and durable. So, for the design criteria, the design of geofoam embankment is adopted as per NCH RP report 529 and NCH RP WEB document 65 Stark et al. 2004. The design chart presented in the paper are only for geofoam with density of 18 kg per meter cube, and when you will design, then you are to satisfy this all the basic criteria. That means you have to satisfy what will be the external bearing capacity, hydrostatic uplift of the geofoam block because it is a superlight material, and hydrostatic horizontal sliding and overturning due to the seismic effect and translation due to the wind. So, you have to check all. So, here is one construction of a geofoam embankment with the slight slope 4 horizontal to 1 vertical. You can see this is the geofoam block and this is the subgrade, this is the roadway width. So, this road thickness, let us say about 610 millimeter, and this is geofoam block, and this portion is to be filled with the soil, which you say that it is a cover soil, and the height of the embankment is h. Now, I will give one example. Let us say safe bearing capacity SBC of foundation soil is equal to 15 kilonewton per meter square. Upwind and downwind slope angle theta u and theta d is 14.04 degree. Pseudostatic horizontal seismic coefficient Kh is equal to 0.2. Traffic load sigma t is equal to 20 kilopascal, and roadway width the RW is 12 meter, and thickness of the geofoam embankment Tg is equal to 6 meter. Unit weight of the pavement gamma p is equal to 20 kilonewton per meter cube, and thickness of the pavement Tp is 0.61 meter, and unit weight of water gamma W is equal to 10 kilonewton per meter cube. Now, height of the water from the front face of the embankment h small h is equal to 0.6 meter. Bottom width of the embankment BW is equal to the 60 meter, and total settlement of the embankment, that is ST, is equal to 10% of the total height, because total height is 6 meter. So, 10% of the total height will be equal to 0.6 meter. Unit weight of geofoam gamma GF is equal to 0.18 kilonewton per meter cube. Unit weight of cover soil gamma cover is 17 kilonewton per meter cube, because generally it is filled up with the soil. Angle of friction between the geofoam and the soil delta is equal to 32 degree, and factor of safety is 1.25, and weight of the normal pressure and the traffic load, that is WP and T, is 21 kilonewton per meter. So, you have to design the embankment considering no tail water. So, I will show you for the design for this embankment. Now, this is the solution. A check of bearing capacity. Now, considering the factor of safety is equal to 3 against external bearing capacity failure. The equation for the required undent shear strength SU is reported by Stark et al. 2004. So, this is the equation. SU will be equal to 3 by 5 into sigma of P, and sigma of P is the normal stress applied by the pavement at the top of the embankment, that is in kilopascal, and sigma of T is the normal stress applied by traffic surcharge at the top of the embankment, and unit is kilopascal, and RW, that is width of the road, and this is also RW, width of the road, plus TGF, that is thickness of the geofoam. This plus gamma of GF, unit weight of the geofoam, into TGF, thickness of the geofoam, divided by 2. So, you have to calculate that what will be the normal stress applied by the pavement at the top of the embankment, that is, let us say here sigma P. So, sigma P is equal to gamma P into the TP. So, this is the thickness of the pavement, this is the thickness of the pavement, and this is the unit weight. So, this is 20 into TP is 0.610. So, this will give 12.2 kilopascal. So, traffic load is given sigma T is equal to 20 kilopascal. So, it is given in the problem. So, SU, that undent shear strength or required undent shear strength, SU will be equal to 3 by 5. This is into 12.2, that is sigma P, plus the traffic load sigma T is 20 into this RW, that is road width is 12 meter, this is 12, this divided by RW 12 plus T of GF, which we call the 5.39. I am just trying to tell you here that so this is the pavement system here, okay, and this the total height, which is 6 meter, and this part is equal to 0.61. So, this height will be 6 minus 0.61, that means this will give that 5.39. So, this is 5.39 and this is 0.61. So, you can write that this, so this is basically geofoam. So, this is of geofoam 5.39. So, T of GF will be 5.39 plus this is unit weight of the geofoam, that is 0.18, it is given, into T of GF, thickness of the geofoam, that is 5.39, this divided by 2. So, this is equal to 13.622 kilopascal, and you know that our bearing capacity is given is less than equal to the 15 kilopascal. So, it is less than equal to 15 kilopascal. So, here is a design chart. So, this design chart for the thickness of the geofoam embankment at various undent shear strength. So, this axis is the thickness of the geofoam and this is the various undent shear strength value for the different top width of the embankment. So, top width RW may be 12 meter, for this top width RW may be 24 meter or top width RW may be 36 meter. This may be 2-way or maybe 4-way or thus 6 ways. So, any way for national highway, okay, which may be the 4 OA, 6 OA, and this factor of safety is equal to 3, and unit weight of geofoam is 18 kg per meter cube. Now, you can have a nature of the curve like this, that thickness is reducing with the increasing the unlaid shear strength of the soil. So, this design chart is for obtaining the minimum thickness or the what will be the height of the geofoam TG for a factor of safety 3 against this external bearing capacity failure of a geofoam embankment. I can give you that one of the small example for this design chart. For the height of the embankment is 6 meter and thickness of the geofoam, that total is 6 minus covered soil I showed you 0.61. So, 6 minus 0.61 is equal to 5.39 meter, and width of the geofoam. That means this is the width of the geofoam. This we talk about. This is what we call the RW. This is RW is equal to, this is 12. This is 12 RW. And the SU can be taken as 13.6 kilopascal. So, you can see here that this is about width of the geofoam is 12 meter. So, let us say consider here RW is 12 meter. So, if you know that 12 meter and you know that what is that thickness of the geofoam 5.39 meter. So, this is here somewhere 5.39 meters somewhere here. So, then you can move horizontally and your width is about 12 meter. So, with about 12 meter, then you can move vertically downward. So, you can see that this unlaid shear strength value SU lies between 14 to something 15. So, which you give this value that 13.6 kilopascal. So, therefore, this unlaid shear strength value, it is less than the safe bearing capacity of the foundation soil, that is 15 kilopascal. Since the SU is less than the safe bearing capacity of the foundation soil, the embankment satisfy the factor of safety 3. Next B, hydrostatic uplift require overburden against the hydrostatic uplift for no tailwater. So, this is the equation O required is equal to Fs into 0.5 into gamma W into H plus St into Bw minus Wgf plus Ww. So, here I am showing you that what is H and what is St. You can see here that hydrostatic uplift analysis with no tailwater after stark ETL. This is the road width, this is Rw, and this is bottom width, that is of Bw. This is Wgf, that means weight of the geofoam embankment, and this is the Ww. This Ww is the vertical component of the weight of the water on the embankment face above the base of the embankment on the accumulated water side, because this side is the water. And here also the U, that U is equal to uplift pressure acting on the base of the embankment. And here is the S of T, that is total settlement, and here is the small h, that is vertical height of the accumulated water to bottom of the embankment. Also you can see that what will be the water pressure also is acting, which may act as 1/3 of this base, so that we do not need here, and this angle is equal to the theta, and this is H is equal to height of the embankment. So we know that this is unit weight of water, you know what is H, ST, you know what is BW, this is road width, here base width, that is B of W, and this is WGF, you know this is W of GF, what will be the weight of the geofoam, and then you know what is WW. Now you have to calculate that W of G of F, that means weight of the geofoam. Now weight of the geofoam, it is like this. Suppose you consider this is the embankment, this is made of the geofoam, and it has the top width is RW and bottom width is BW. So it is given top width RW is given 12 and bottom width BW is given 60. So it will be half into 12 plus 60, and the height, this is like a trapezoidal. So you can measure that what will be the area, that means half into 12 plus 60 into height is 6. So height is 6 into the unit weight of the geofoam, that is 0.18. So if you can calculate, then you can have the WGF is equal to 38.88 kilonewton per meter. Similarly, you have to calculate what should be the WW, that means weight of the water. So this is the weight of the water here, this is the triangle here. So this distance is H and this distance is HT. So this ST is generally we have considered the 10% of the height H, that means 0.6. So this is ST 0.6 and this small h also given in the problem is 0.6. So this height will be 0.6 plus 0.6. So 0.6 plus 0.6. So that means it will be 0.6 plus 0.6. So half into 0.6 plus 0.6 into this angle is equal to the theta. So theta, this value is 14.4 or 14.04 or 14 degree, approximately 14 degree. So this is tan of 14.04 degree. So into 1.2, because this to here, that is 1.2. So this is theta. So it will be 1.2 divided by tan of 14.4 will give you this. So while it is written 1.2 divided by tan 14.04 degree into that unit weight of water is 10. So if you can calculate, then you can have WW is equal to 28.79. So this is the area of that triangle and the unit weight of the water. So you can have this value. So you know now that what will be the weight of the geofoam, what is the weight of the water. Now you substitute this value in this equation. So O required will be factor of safety given 1.25, then this is into 0.5, again gamma W is equal to 10 into H plus ST, I say 0.6 into bottom width is 60, that is 60 minus WG plus WW. WG is given 38.88 plus WW is given 28.79. So it will give 382.33 kilonewton per meter. So this I told you that what is hydrostatic uplift analysis with no tailwater. Now this is the design chart. This is design chart has been made for hydrostatic uplift with no tailwater. So this design chart is, this is the accumulated water level or by embankment height, and this is the required overburden against this hydrostatic uplift, that is in kilonewton per meter. So, this also road width is 12 meter and the unit weight of geofoam is 18 kg per meter cube, and for different H value, that means H may be 1.5 meter, 3 meter, 6 meter, 9 meter, 12 meter and 15 meter. So, here it is given. Okay. So, from this design chart for thickness of the geofoam, let us say 6 meter. So, your height of the embankment is 6 meter. If height of the embankment is the 6 meter and the ratio of accumulated water level to embankment height is 0.2, it is here 0.2, and then require overburden against the hydrostatic uplift for no tail water. So, from 2 then you move for the 6 meter height of the embankment. So, you can have some value what is called the required overburden against the hydrostatic uplift for no tail value is about 382.3 kilonewton per meter. So, from this design chart you can calculate that what will be the required overburden against hydrostatic uplift with no tail water. Again, that O required is equal to gamma P into Tp into Rw minus gamma of Gf into Tp into Rw plus W of Cs. So, here that W of C of S, how you can calculate the weight of the covered soil. So, for the weight of the covered soil, I can show you that how this weight of the covered soil WCS has been determined. So, this is the covered soil. Now, this covered soil, suppose this to this is what we call the H cover. Okay. So, this H cover is the vertical thickness of the soil cover. This vertical thickness of the soil cover. Whereas this is also soil cover. Okay. This is, let us say that this is T cover. So, this is the perpendicular thickness of the soil cover. So, this and this is not the same. So, this is H cover, that means vertical thickness of the soil cover, and this is the perpendicular thickness of the soil cover, which is T cover. And you know that this is the thickness of the geofoam, that is T of this thickness of the geofoam, that is called the T of G. And also this is the, let us say, L cover. So, that means this is the length of the soil cover on the side of the embankment. So, we have to calculate that what is W cover. So, to calculate the W cover, you can write this equation. W of cover is equal to 2 into gamma of cover into T of G divided by sine of, and this angle is equal to theta, that is about 14 degree. So, this into sine of theta into T of cover divided by cos of theta. So this is 2 and gamma cover is given is equal to 17 into thickness of this geofoam 5.39, this divided by sin theta means sin of 14 into, now we go for the T of cover, okay, and this is also cos of, this is 14 degree. So now we will see how you can calculate that what is called the T of cover. To calculate the T of cover, you can see here you wanted to calculate that what will be the T of C. T of C is here, okay. This angle is equal to theta. This angle is equal to theta. So this T cover will be equal to H cover into cos of 14 degree. That means T of cover is equal to H of cover into cos of 14 degree. So this will give H cover 0.61 into cos of 14 degree. So this will give 0.59. So you know that T cover will be 0.59. So you can write this is 0.59. So now I am just showing you here that W of cover, that is 2 into gamma is 17, this into thickness of the geofoam 5.39 into, this is the T cover, thickness of the cover 0.59 as we calculated. This divided by sin of 14 degree into cos of 14 degree. So this will give 460.6 kilonewton per meter. So again gamma P into Tp into Rw minus gamma Gf into Tp into Rw plus W of Cs, weight of the cover. So this gamma P is 20, Tp is 0.61, Rw is 12 minus gamma Gf 0.18, Tp is 0.61 and Rw is 12 plus WCS is 460.6. So this will give 605.68 kilonewton per meter. Therefore, O required is 382.32 kilonewton per meter, which is less than 605.68 kilonewton per meter. That means it's okay. So overburden force provided by the soil cover can effectively resist the hydrostatic uplift of geofoam embankment. Next, see hydrostatic horizontal sliding. Require overburden against hydrostatic horizontal sliding for no tailwater can be determined from the following equation. That is, O required is equal to Fs, that is factor of safety, into 0.5 gamma W into H plus S T square divided by tan delta. What delta is equal to friction between the soil and the EPS geofoam plus 0.5 H plus ST into gamma W into BW minus W of GF plus W of W. You know all the term, what is H, ST, gamma W, BW, WGF and WW. So O required is factor of safety 1.25, this is 0.5, gamma W unit weight of water 10 plus H is equal to 0.6, ST is equal to 0.6, so 0.6 plus 0.6 square, this divided by tan delta, delta value is given 32 degree plus 0.5 plus H plus ST 0.6 plus 0.6, then gamma W is 10 and BW is the base width of the embankment, that is 60, minus this weight of the geofoam we calculated earlier 38.88, and also weight of the water, that is WW, also we calculated 28.88, earlier also we have calculated. So, you can obtain ore required will be equal to 306.7246 kilonewton per meter. Now, this is the hydrostatic sliding with no tailwater. So, here this accumulated water level by embankment height 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and this is required overburden against the hydrostatic sliding. This is road width considering 12 meter, delta value is 32 degree, and the unit weight of geofoam is 18 kg per meter cube, that density of the geofoam, and the height of the embankment is 1.5 meter, 3 meter, 6 meter, 9 meter, 12 meter and 15 meter. So, you can calculate that what will be the required overburden against this hydrostatic horizontal sliding for no tailwater. So, here for the design chart, for thickness of the geofoam is 6 meter. So, this one 6 meter, and the ratio of accumulated water level to the embankment height is 0.2. So, from the 0.2 you move up, or the H is equal to the 6 meter, and then you move horizontally. So, require overburden against the hydrostatic horizontal sliding for no tailwater, you can have 306.7 kilonewton per meter. So, you can see also here that what we receive 306.7246 kilonewton per meter, and from this also design chart you are having the required overburden against hydrostatic horizontal sliding for no tailwater is 306.7 kilonewton per meter. Again, O required is less than gamma P Tp into Rw minus gamma Gf into Tp into Rw plus W of C of S. So, gamma P into Tp into Rw minus gamma Gf into Tp into Rw plus W of Cs. So, gamma P is 20, that is unit weight of the pavement is 20, and thickness of the pavement is 0.61, and Rw is equal to the 12 minus gamma of Gf, unit weight of the geofoam is 0.18 into, this is thickness of the pavement, that is 0.61 into Rw road width into 12 plus WCS. So, which we calculated the what will be the weight of covered soil, that is 460.6. So, this will give that 605.68 kilonewton per meter. Therefore, O required is 306.7246 kilonewton per meter, which is less than the 60568 kilonewton per meter. That means it is okay, because O required we calculated 306.7. So, it is less than 605.68 kilonewton per meter. So, overburden force provided by the soil cover can effectively resist the hydrostatic horizontal sliding of the geofoam embankment. So, here some idea that how you can design that if the water level, it may be on the one side it is considered. Sometimes for the embankment construction you can also design for the water level at the both sides of the embankment too. So, with this I finish my lecture today. Let us hear from you any question, and thanks for listening.